So, page 6 of your booklet says the temperature of start. So when a substance is strongly heated, a whole range of wavelengths is usually given out to form a continuous spectrum. We know that when you look at white light, you can see there's a continuous spectrum included in it. And when you send the light through a prism, you can make a rainbow. Put them down for now. Okay, so these spectroscopes that we're going to use in the glasses, they do the similar kind of thing. They split the light up, okay? But we can look at how much of different parts of the spectrum is in the light, and that will tell us a bit about the light and where it comes from. So the amount of light of each colour that is emitted depends on how hot the substance is. When it starts to glow, an object may be described as red hot, but if you get hotter, you can describe it as white hot. White hot's the most dangerous. So metal workers can judge the temperature of steel not by noting its colour. Astronomers can judge the temperature of the surface of a star by noting the colour of the light that the star gives out. And the most commonly used technique for analysing visible light is called spectroscopy. This involves breaking up light into its individual colours, and we can use a spectroscope to do this. Okay, so the first experiment, we're going to look at this bulb over here. And I have got, hopefully this is going to still work, my camera set up so the people at home don't miss out on this, with one of the glasses on my camera. Okay, so what I'm going to do, so those glasses that you're wearing, or you may be wearing, is on this camera. Okay, so you can look at this, you can either look at it through your glasses, it's a bit easier to see through the glasses, or you can look at it through a spectroscope. Okay, so this bulb, I'm about to turn it on now. Okay, so as soon as yeah, that helps that my camera is frozen, so let's try to open that again. Right, okay. That's still not working. Great. And that's helpful, isn't it? Right, let's see if we can change the camera screen. There we go, right. Nope. Right, we'll just use this instead. Okay. So, hopefully, let's just tap this on instead here. No. One over there. Right, okay, so hopefully this will now work. So, as you look through the glasses, or the spectroscope, you can see the colours. Okay? So, as we'll start off with kind of low. Okay? So we can see with the low one, we've got quite a lot of red and green, not much blue in that one. So as I move it up, the red is kind of dimming up a little bit and we're getting more blue. Even more blue, but not much red at all. That's it, it's the brightest. So we can't, the red's basically gone, but we're seeing lots more of the blue. Okay? Okay? So as we go through the spectrum, as we go through the different heats, we can see more red here with the lower temperatures and more blue with the higher temperatures. Okay? And that's exactly what astronomers look for. They look for the amount of blue, the amount of red in the spectrum. Right, so let's go back to our notes. Yeah. Okay? So, I'm not talking over anyone, we can always stay behind. You'll be using the glasses and spectroscopes again very shortly, but we're going to fill in this. So, to investigate the continuous spectrum of a bulb using a spectroscope or the glasses, they work in the same way. So, in our observations, as the brightness of the bulb increases, its temperature obviously also increases. Page 6. And more light is emitted at the blue end of the spectrum. Violet light has a smaller wavelength than red light. As the temperature increases, the wavelength of the light emitted becomes smaller. Okay, so basically astronomers look at the light coming from stars and they can tell the temperature by looking at the colour, more of the colour. So if there's more blue, then it's hotter. If there's more red, then it's cooler. It's still very hot, but just not as hot. So the colour of a star depends on its surface temperature. And look at the list below and put it in order of increasing temperature. So order of increasing temperature is order of colour. So the lowest is Barnard star, the red one. So that's your sort of lowest temperature. Then it's the sort of orange-red one. Then it's the yellow one. And then it's the bluish-white one. That's the hottest one. And I've got the actual temperatures here. So Barnard star is 3134 Kelvin. You don't need to remember these, by the way. The sun is 5,778 Kelvin. Rigel is 11,000 Kelvin. And Betelgeuse is 3,500 Kelvin. Can you see it? Like, astronomers can see it through the telescopes, yeah. You shouldn't be looking, no, you shouldn't look at the sun directly anyway. Like, you shouldn't look directly at the sun anyway, but you can look at the sunlight and you'll see that you can see a spectrum in it, yeah. No, they're not the same. They look similar, but they're not. Okay, Finlay. Okay, so where does the light produced by glowing objects come from? Now, this is an extension, this isn't in the course, but I did ask you to have a read through it at the start of the lesson. But it's just for interest if you're interested in it. So you can take your glasses off just now. Gregor? You use them later, Finlay? Maria? Yeah. So light often comes from hot objects, so the sun, the filament in a lamp, etc. It can also come from things that are cold. The phosphor dots in a TV screen, the glowing of a neon light, etc. The light is produced in the same way by giving energy to atoms. So basically what happens, I know my photocopy, my printing isn't great on this one. What happens is, it's all to do with electrons in energy levels. So those of you that do chemistry will probably know about this already. But electrons don't just orbit randomly around atoms, like the centre of an atom. They are in little energy levels. Okay, and those electrons can sometimes, when you give them energy, they can jump from one energy level to another. So quite often you can get energy electrons jumping from here to here. Okay, but electrons tend to want to be on the most stable level, which is the one closest to the nucleus. So they can jump up here, but they require some energy to do that. But quite often they'll just fall back down again. And when they do that, they give off energy, and that's usually in the form of light. So that's where you get the light from. So if an atom is given the right amount of energy, an electron can jump up to a slightly higher energy level. After a short time, it falls back down to its normal energy level. As it does this, it releases its energy as light. A small jump gives out a small amount of energy, so a lower frequency light, and a larger jump gives out a large amount of energy, so a higher frequency light. So that's higher physics. We would definitely do that. Well, I'm doing that with my higher physics class almost at the moment. But that's sort of just for interest. That's where different colours of light come from. Yep. So wavelength is inversely proportional to energy. So frequency is proportional, but wavelength is inversely. But yeah, good question. Right, okay, so We're going to do a little bit more spectroscopy now. Okay, so the visible spectrum, you've all seen now that if you look at a white light through your diffraction glasses, your glasses, or through your little spectroscopes, you see like a rainbow, okay, a spectrum of, and we call that continuous spectrum, that rainbow, okay. So when white light is passed through a prism, the light is split into the colours of a visible spectrum. White light consists of different colours, each with different wavelengths. The prism refracts short wavelengths more than long wavelengths, and that's why you get the rainbow through a prism. So continuous spectra, many light sources produce a continuous spectrum containing all the wavelengths of visible light. So a rainbow is a continuous spectrum. Okay, so an example of this is this type of source is a standard light bulb. So again, so something like this light bulb that we looked at, and this one over here. You can look at in your glasses now. You see a continuous spectrum through those glasses, the rainbow effect. Okay. So we're going to look at it again in a second. But you don't always get a continuous spectrum. So you get a continuous spectrum if you're looking at white lights. But you can also look at different types of light and you'll get different spectrums. So you only see some of the colours. Okay? So a light emission spectra. So where we know that all atoms give off light when they're heated to high temperatures. The atoms of any particular element give us especially large quantities of radiation at certain wavelengths. As a result, the spectrum of that element has bright lines, called spectral lines, at those wavelengths. So they've got bright lines at certain colours. Okay, not all the colours, just at certain colours. And we're going to look at some of those in a second. You'll see those sort of things that are around the room. We're going to look at those in a second. So each element has a pattern, a very specific pattern of spectral lines that differ from other elements. Okay, so each element has its own specific pattern of bright coloured lines. So astronomers can identify the elements that are present in stars by examining the spectrum produced when the light from a star is viewed through a prism or a spectroscope. Okay, so we'll do an example of identifying elements in stars in a second, but I would like you to have a look at some of these. Now, this is a bit tricky with social distancing and stuff, so what I'm going to do is I'm going to turn these on. And so that one there, this one here, no, it's not a beam. This one here, they are all different elements. Okay? So what I like to do is you need to make sure your distance from people don't get affected, they don't get up in their own face. Okay? You can still have a look at them, but please, as I said, don't overrush the one, just take your time. If you're done with one, move away from it so someone else can have a look at it. Okay, so you move around the top piece while you use spectroscopes as well as glasses. What's the difference? Nursing, very difficult side. It looks to feel more a thin line. It's not quite the same as the glasses. The spectroscope, by the way, I've not been used by anyone for a long time, so don't worry about it. By the way, if anyone wants to take photos with their phones, it takes really good photos if you put the glasses in front of their phone. Remember, don't all crowd noise once you want to look at it. Right. You've got 2 more minutes to have a look. Yeah, put the glasses in front of your phone camera and you can take some good photos. It's, that's why I usually get the glasses out because like spectacles. Right, okay guys. Right, I'm gonna get this time lapse up on you, okay? Okay. Right, listen. What I would like you to do now is please bring your spectacles, put them back in the bags or the boxes, and your glasses and put them in the tray at the front for me. Put it back. You can get them on the internet, yeah, you can get them from the internet. Oh, they're not expensive glasses. Okay, have a seat. Finley, go and have a seat. Have a seat. Okay, Finley. Okay. Right. I'm waiting. Yes. Okay, so we're going to go through an example of how we can use those spectrums to identify the elements in a star. So the next page, page 9, is the type of question you might get asked on this. So by analysing the spectrum of a star, astronomers can identify the types of atoms that make up the star's gaseous outer layers. The spectrum from a star is a line spectrum made up from the spectra of all the elements that are present. In addition, the spectrum of a star or planet reveals the relative abundance of the various atoms and molecules that are present. If one element or compound is more abundant than the other, so there's more of them, its characteristic spectral line will appear stronger or brighter. Right, so the spectral lines of light from a distant star are shown below in figure 1. Figure 2 shows the spectral lines of a number of elements that have just been studied anyway. Use the spectral lines in figure 2 to identify which elements are present in the star. Now the best way to do this is you get yourself a ruler and you identify, you basically go along and you go, right, what elements, so you go to each element, you go, is this in my spectral line? Is this in my given spectrum? So we look at hydrogen first of all, right? So that line is in the top one. That line is. That line also is. This line is. This line is. And this line is. So hydrogen is in that spectrum. Let's check helium. Okay, so take our ruler. That line doesn't look like it matches. That big thick line isn't in there. That line isn't in it. So we're pretty sure helium is not in that spectrum. Let's have a look at sodium. Yep, that matches. Those two match. That matches. Those two thick ones match. Yes, so sodium matches. And let's check the mercury. Well, we've already got two thick lines that aren't in it. That line's not in it. So a few of those lines are not in it. So mercury's not. So it has to match completely. So we've got two things in there. We've got hydrogen and we've got sodium. Okay, so it is quite a nice gift of a question if you're given it, because all you do is you're just matching basically. Just nice matching. And number two, during the lifetime of a star, a nuclear reaction takes place within the star in which lighter elements are fused together to make heavier elements. So stars start from the lightest of elements and then they move on and they get heavier and heavier. So which elements would be in a very young star? Which are the lightest elements that we know from chemistry? Helium, hydrogen, yep. So you could tell something if a star is quite young if it has a lot of hydrogen and helium in it because it's the lighter elements. If they've got a lot of heavier elements in it, then it tends to be a bit of an older star because it's gone through more nuclear reactions. Okay. One last page and then you guys are going to do some questions. So, line absorption spectra. Now, I do apologize again for the copying here, but we have looked at two types of spectra so far. We've seen the continuous spectra. That's the rainbow. Okay, that's all the colours. Lovely, continuous. The emission one are bright lines on a black background. Absorption, you can just about see it here, are black lines on a continuous background. Okay? An absorption spectrum happens when electrons absorb some energy so they can move. So this line absorption spectrum, this type of spectrum is obtained when white light from stars passes through gas clouds in space. When gas clouds absorb specific frequencies of light, black lines appear in the continuous spectrum of emitted light. The absorption spectrum can be used to identify the elements present in the gas cloud. Okay, right. So I would like you to have a go. There's only one question, I think, on this type of thing, and then we're going to go back. So, question booklet, page 3 is on the spectrum, and then if you go back in pages 1 and 2 as well, so you don't get to do that. Maybe towards the end of the term.